Okay.
Okay.
Thanks for catching that.
Oh yeah, thank you.
I wonder how much it missed.
So yeah,
You'll see.
this is all
will
that
see,
falls under the problem of tuning the hyperparameters. Okay, and you just have to go a trial and error method. So this is the first part where you're just setting up the structure
So
of this.
your contribution is the trial and error part?
No.
Okay.
No. After that, you've got different things like setting up the neurons and then the activation function.
So now, what do the number of neurons in each layer correspond to with respect to the data set?
It does not have any linear relation with the data set. Okay. What neurons essentially does is it actually gets the most important features of the data set and tries to pass it along to the next layer.
So all neurons get the same information?
No. Every other neuron gets trained for a specific feature. Okay, so say
you decide that, or?
that is the way how backpropagation is training the neurons.
Okay.
So they are getting not versatile. They are getting just better in some specific feature of the data set. Okay, so this neuron, so for example, you're trying to recognize a picture of a dog. So one neuron will be recognizing the eyes. Okay, the other one will be getting better in just recognizing the ears. The other one will be recognizing the color.
But here you have only one thing called rotation, latitude and longitude.
Yeah.
So you don't have many features to
Exactly.
to train.
Right.
Right?
No.
I mean, you cannot do latitude and longitude.
No.
You have to do
So-
it together.
No, the
What you're
input
training on
features
day
are
of the
more than that. Just the output is the language.
No, you're training on day of the week too, right?
Yeah. So
Yeah,
it's
it
got-
has
Correct,
more.
that is input.
No, yeah.
Yeah, right, yeah.
Correct, but
So does every neuron have the same
matching
equation?
eyes is like matching latitude.
So
and
does
longitude.
every,
Does every neuron have the same equation in it?
the neuron has
Then
the
you have
input-
another layer
Every
that's
one of them
matching day
has
of
the
the
same,
week and time of the day.
The neuron is the
No,
whole
that's
network or
input.
one node in the network?
So
That's input.
neuron, there are
Yes, you're right.
multiple neurons. There are hundreds of neurons
Output
in
is
one
only
layer.
Right, but they all have the same equation.
They all have the same equation.
Outputs.
But they get different inputs.
But he may
So
take
Yes.
a
they
subset
focus
of the
on
data
training
set and do the
different
same
parts
thing.
of the equation.
I think I should get into.
Granularity.
No, I understand.
So the features that we were talking about are these. Okay, and based on this, the model is just getting this. Okay, and based on this, it is trying to predict this. Okay, and whenever it, so how does the model know it's not behaving well or it's not behaving right? Because then the supervision comes. Because we've got a ground truth sitting next to it, next to the output value, which is the y prime, and that's why we say it y prime, because it's not the ground truth. The y is sitting next to it, through which it sees that how much of a difference.
It's a control feedback, right?
Exactly.
Okay, can you skip
Yeah.
back to where
Control system.
So moving ahead, this is what you're talking about, and this is what it looks
Here
like.
is a very funny question. So you said you have to determine the number of layers. So there's no deep learning algorithm for that?
Okay, so there are different approaches through which
That's where you need deep learning, right?
there is, and I already promised I'm going to answer you that question. So.
You're kind of running out of time.
Yeah.
So this is what a regression looks like, because at the end you've got a one node or two nodes for either just one location or latitudes and longitudes. Moving ahead, this is a cost function. How does the model know that it's not doing well? It's just a simple mean square error cost function. Why mean square error? Because this is smooth and is guaranteed to give global minimum. Now you ask me what is global minimum. So if a cost function is supposed to be drawn as a function, okay, all these bottom downs that you see are the minimum of the
I think we
errors.
all know that concept.
Okay. Let's go ahead. Okay, so next is classification, and to begin with classification, I just want to explain that difference between mutually exclusive classes and non-exclusive classes. We are dealing with the mutually exclusive classes, which do not, so a value within that class will not belong to any other class. And this is a very important concept in terms of understanding the cost function of the classification, is that we do one hot encoding. That is, if a location belongs to class A will get 100% probability, rest will be 0. So that is just one hot encoding or dummy variables. Moving to classification, what we do is we are using a softmax classifier. A softmax classifier distributes a probability distribution over all the classes. It takes the sum of the e to the power of the output of all the classes, and it takes the e to the power of the output of the jth class that it's trying to predict and looks for its probability, that how much of its probability of occurrence is in the data set.
So this means you cannot weigh different features differently?
Well, here we are talking about all the neurons, okay, that the output that is coming out from the neurons. Here the features are actually boiled down to a certain element that the neuron has understood from the entire data set, which it thinks that, okay, so this observation that I just saw belongs to class
So
1.
the output is uniformly classified,
Yes.
not necessarily the input.
Not the input, but the output. So what it does is, like I said, it imparts probabilities, give distribution for each target, and finding out most classification where probability class is maximum. Once we are through with this, this is what it looks like. So this input vector, so weekday, hour, precipitation, temperature, and something also else, goes to the entire neural network. Okay, this is a class. This is a layer that gives the final output. The softmax layer. So at one time you are just showing one observation that will be comprising to one specific class. So the softmax thinks that out of these 5 classes, I think the first class has the one which has the maximum probability, and that maximum probability is taken as the predictive class. Now, how do we check that? What is the cost function which is associated right here? Here is something that is known as categorical cross.
So the output of the neural network goes to softmax?
Yes. Just to see that what is the probability of...
So the output of the neural network is lat long, right?
No. Here right now we are talking about classification.
Oh, okay.
Here are the clusters.
Okay.
Here are the clusters. So the cost function associated to this is the categorical cross entropy. Like I told you, all these, the one hot encoding that we had, so say for example, we were trying to classify class 2 here, and that's why we got 1 here, because 1 is 0, 3 is 0, and 2 is 1. And the predicted class also had the maximum probability of class 2, okay? Now because categorical cross entropy knows that this observation is for the class 2, it's going to multiply these two, and these two will be 0, and it will see that how much of a difference is between these two predicted class. What it's trying to do is, it's trying to train a machine that whenever a certain class comes into the neural network, it tries to predict that class with a 1 probability, nothing less than that. So that's why it's trying to punish the model to be more closer to the predictive class. So that's what the cost function for the classification is, and why can't we use MSE for classification, which is categorical cross entropy. The most important thing, the experiments. The experiments were done on the American dataset, which we named as to our dataset. It has almost 9,000 GPS points, collected for 6 months using Google Timeline, and we added the weather using NOAA weather website. System configuration, we are using TensorFlow.
So this is your data set?
Yes. We've got TensorFlow and Keras as the packages. We are using Tableau, Seaborn, and Boca for the visualization. macOS, and right now we are not using GPU because the data set is not too huge, and it's if and when required. So the multiple linear regression model configuration is the hidden layer. So this was the trial and error method. Okay, so the hidden layer, 3 hidden layers, each have 6, 4, and 3 neurons. Activation function of tangential hyperbolic. Tangential hyperbolic is the one which goes from -1 to 1. Okay, and it gives you a range of values between that. So the output layer has 2 neurons because we want to predict one latitude and one longitude, and it's going to be pure linear. So whatever neural network thinks is the one that we accept. And the cost function is mean squared error along with the optimizer or stochastic gradient descent. So there were 2 sets of experiments done. We wanted to see that how temperature and precipitation are making a difference in the data set. So in the set 1, we just took month, weekday, and hour, and we said neural network predict the latitude and longitude. In the set 2, we took month, weekday, hour, temperature, and precipitation, and based on that, we predicted latitude and longitude. We already had a good feeling that temperature and precipitation is going to make a better difference, but we didn't know yet. And the classification model had 3 different hidden layers, 5 neurons each, tangential hyperbolic, and the output layer was supposed to be as number of total clusters. In our case, were 9 clusters, and we had softmax classification, like we just mentioned, softmax activation function, and we also explained what categorical cross entropy does, and stochastic gradient descent was used for the training algorithm. So the American study, the results for the multiple linear regression without weather and with weather. So this one is without weather. What we see here is after maybe 15th or 16th epoch. Epoch is number of times that you have shown your data set to the model. After that, the model tries to get down as much as possible, but it almost gets a certain stability after, say, 50th epoch. This was without weather, and this was with weather and time. But if we just try to see them together, this is what it looks like. The blue is without weather, it's only the time as a feature, and orange is with weather. So that is temperature and precipitation. And we can see that it actually gets down before even the time tries to get down there, and it always goes below. So the loss is actually very much better when we are adding features like temperature and precipitation, which actually tells that how good of the predictors temperature and weather could be in one's location identification. And this is the validation data. So till now what you were seeing was just the models data on the training data set. This is the validation data. So if you see, without weather, the validation data is not even getting close to what with weather can go to. So as per the loss function for the validation data, and mind you, for the validation data, we have 30% of the entire data set.
So this is the error with respect to the expected value?
Yes, yes,
Hmm?
And it's a log loss, so whatever the loss was, it was the absolute, the mean square
So
error.
did you do, I wouldn't say cross-validation, but
Yes,
you added temperature and precipitation
yes.
because you had someone, but did you hold back two other attributes and see whether that gives the same thing? Which, like, you know, you have 5 attributes, right?
Mhm.
You had 3 and 5.
Right.
1, 2, 3, 1, 2, 3, 4. I would have done 1, 4, 5
Okay,
and
okay.
1. Because now I don't know whether it is because
Oh,
of that
yeah,
or
that
it
would
is.
be an interesting
Yeah.
experiment to
Yeah.
take different combinations of the attributes.
Yeah, you have to show
So
that,
that's
right? It's
the
not,
the
it's
features,
like
yeah.
cross validation, but at a
Okay,
variable
that's
level.
something you can do for
Yeah.
Yeah,
the,
that's
It's
easy.
easily
before
doable.
the fence, right?
Makes
Okay.
sense. Yeah, thank you. Yeah. So for now, it wasn't done, but what was done was just time and weather, because we thought of these two as separate classes, but this makes actually sense. So we can actually,
So does this show that with error, with precipitation and whatever temperature,
yeah,
it showed closeness to the target?
yes, that's what it shows, because the more less loss you have, the more closer you are to the ground truth. That's what it says. Here the difference is a huge difference. This is not anywhere getting to 0, because here is what the ground truth is lying, right? And here you got a huge difference as compared to this guy. So, and this is with weather and
Correct,
temperature.
but this, so I don't know whether you guys do it in this one, in other cases, you do, what is that, NPD or something, where you have a rank of things, so here maybe it's, and then you get your rank, and then you want to see how close this rank to this one. So you do some distributed value, but here it is difficult to see because some of them may be correct,
Right,
some of them may not be correct.
right.
So you don't know what percentage it came out the same and what percentage didn't come out the same.
Right. And that's the biggest problem in regression, because you're trying to see how far the value is from the ground truth value. In
Yeah.
terms of classification, there we can actually look.
I mean, how far is one thing, but also can you say what percentage it matched versus what percentage it didn't match?
That is a case when we try to, which we try to answer in the classification cases. Because there we are trying to classify each location into a separate cluster, where we can also find the confusion matrix, right? Where we can say that this class matched to its own class 1,000 times, and it matched to another class maybe 12 times, and matched to another class 20.
Yeah.
That is what we have done in classification. I don't know if I have, I think,
Go to the next.
okay.
Okay.
Now the classification accuracy, and we are also comparing. So at this point, we were convinced that temperature is actually playing a very important role. So we did not do the same thing with the classification. Instead, we added the entire 5-feature data set, and we did something else, which was the comparison with the other classifier. But we look at the accuracy first. So the training accuracy is pretty good, and the validation accuracy after 9th epoch crosses the training accuracy. That proves a point that the model is not overfitting. It's not just learning everything, and it's not just cramming up.
What is it? This is for the.
This is for the classification.
Okay, so this apart, 9 people, so where does the people, oh, 9?
So this is epoch. Epoch
Okay,
is
how many?
how many times you have shown the data to the model.
Okay.
So 1 time, 2 times, 4 times, 6 times, and so on and so forth. After you showed the data to model 10th time, the accuracy was almost 84%, and along with the validation accuracy being exactly 84%, and after that the validation accuracy kept on rising. That says,
shouldn't be the case that as the hypothesis increases, it should converge to the actual accuracy,
that's the biggest problem.
rather than diverge from the actual accuracy.
Well,
Isn't that the case?
that is, okay, so I would have to investigate that more. I cannot just say anything right now.
Okay,
But-
because that's what you expect.
Yeah, you would expect that.
Yeah.
I mean, the neural network doesn't behave normally, I think.
That's,
Because it's a very artificial
I
structure.
know, I mean, I have my apprehensions about
So I would-
I know it's very widely used.
Yeah.
it would have made much more sense if the training accuracy would have just gone to 100% after a point, right? And the validation accuracy would have tried to reach to training accuracy. But I would have to investigate that in a moment.
We need to get close to wrapping up.
So here is something that you were talking about, is the precision recall F1 and the support. What you see here is the validation data, the testing data. So here about 20% or 30% was 1454 of the entire data set, and the precision was 88, and the recall was 89, and the F1 score was 88. But what we see here is pretty good. This guy here is on an average 1.4 times better than random forest classifier given the same data set to all the models. Random forest classifier, support vector machines, and k-nearest neighbors. And this is the validation data. It is not even the model's accuracy. It's after the model has been trained, and it's actually trying to predict what class is going to be at.
Correct, but the model was trained on your data set, right?
Right.
So is it fair to come, if you train it on another data set and then use it on your data set, you may see the same.
No, that cannot ever work in this world. Because in that case, the model is trying to learn somebody else's function.
I know,
Looking at-
no, correct, but if you have trained it on your data set,
Right.
how can you compare it with another data set?
No, I'm not comparing it with other. This is all trained
Same-
in my
same
own
data
data
set.
set. Yeah. This is trained in American study, American study, American study, along with American study. And this is
Okay.
all being tested on the validation data of the same study. So it's not that the model have already seen the data.
So their best model gave this percentage?
Yes. So random forest classifier was 66%, support vector 65, and k-nearest neighbor, the worst, 58%. And yeah, so these were the three models besides our model that we compared the model on, and that was the classification report on the validation data for the multi-layer perceptron. So moving ahead, other future works that I plan to work on. Lately, a month ago, I was studying about this new type of time series neural network. It's known as LSTM. It's a recurrent neural network. It's not alike whatever we have talked about here. It's a recurrent neural network, and that's because the output of the data or output of the model goes back and feeds as an input to the model. So it keeps on taking the model and it keeps on predicting whatever you are trying to make it predict. The best part of long short-term memory is, we'll talk about it in detail more, but for an instance, for a layman, it's very well to understand that a model that has its own memory. So LSTM models are the ones which have a kind of their own memory, so that they can make predictions based on the time series. Okay, that can be, one of the example is speaking to somebody. Okay, how machines do speak with us, and based on the purpose and the concept of the talk, it talks because it has learned how to form words based on a long string. And that's what came to our minds, that how about we use LSTM in terms of location prediction, because where we are going to be next is highly dependent on where we have been in probably past hour, past 2 hours, or even past 3 hours. And that's what the idea came to us. We even did a couple of experiments based on this, but in the currency exchange rates. What we did, we took past 30 years of Indian and US dollars currency exchange rate, and just based on time. There's nothing else. There are thousands of other features that affect currencies, but we just wanted to see that how well it can behave.
Based on what?
Based on just the time. So
Time, okay.
yeah. So because currencies depends upon GDP, profit, whatever, thousands of the
Well, if
features.
you can get a good model, you don't have to worry about your PhD.
Yeah.
So I really want to show you the results. I can probably show you after the meeting, but yes, that actually really worked well. It also got published on Medium. Medium is a neural network and machine learning community where they allow you to publish your blogs and whatever. But that's what the idea came, that how about we use LSTM in location prediction. We did a small experiment, but it shows us a very promising result. The work is still in progress. We are trying to get it published first, and that is one of the future works.
Public first and
So
then do the work.
So you are promising that this is will
Yes,
be done before
yes,
the defense?
Yes,
Okay.
I am promising you
But
that.
you have to be clear about this.
Yes, yes. This is one of my promises, that I'm going to build an LSTM model that can actually, and I cannot promise that, I can try that it surpasses the accuracy rate that what it is doing at this current stage. The next thing, which is very, how do I say, very ambitious, because it's just in its early forms. It's the evolution algorithm. Everybody is working on it. The current research, they are working on Google Brains right now. Evolution algorithm is the one that I'm now going to answer your question. Okay, so the idea comes from the genetics algorithm from biology. How do humans evolve? Okay, you've got two couples, they mate, they get their offsprings. Their offsprings has the features of the two couples, okay, and based on that, the offsprings behaves in the current world, okay. Similarly, if the concept can be combined in neural networks, that we've got a population of 1,000 neural networks made into different models and different features, and we start mating all these neural networks and getting all the offsprings, and there is a, the one who is fit survives, okay? That kind of theory in neural networks. The optimization algorithm has already shown a very promising results in making the optimization in hyperparameters. The answer, how do we set number of neurons? How do we set the number of layers? What is going to be the activation function? We are just going to mix different neural algorithms or different neural models which are the best in that specific field and make one which has all the capabilities of all the neural networks which is actually performing well. This is going to be very ambitious, but I'm going to try my 100% in it.
So there is an optimization algorithm for combining neural networks?
No, not yet. There is no one algorithm which is available outside.
I mean, isn't the problem, I don't know, the issue there I see, so genetic algorithms are there, but we understand a lot about how the basics of the genetics and how they combine.
Right.
The number of chromosomes. In the neural network, this is the biggest problem I see as is, okay, you have done all this, you've got, but you still don't know why this prediction, what is this prediction based upon? No clue. And you will never ever be able to know why it works.
Explanation.
Huh?
Explanation.
Yeah, that is the biggest problem with neural networks, right? It works because you have tweaked so many knobs, but you cannot explain why it works. Right? Is that correct?
The biggest problem in that case is the high dimensions of the data.
It has nothing to do with the dimensions, it is just the way it works. There is no explanation because you've been tweaking, changing things to the point why this combination is better than others in terms of understanding the input data and the output. I mean, that means that was the problem, but again, the other thing is for every problem, this has to be done separately.
Right.
Right? Because there is no general solution.
Right.
Yeah, well,
This
when
solution.
we were talking about some of the research we could do, that was one thing we were thinking about a while back before we focused on this,
Right.
is to see for different kinds of data and different kinds of problems, what are the most
I know, but
best
he has to go
algorithms.
through the same process to do that.
Right, right.
And you will get another
But it
neural
would help
network,
people
but
to say if my
we
data
cannot compare this
is
to
in
neural
this
network.
way, I could use this functions in the neuron. If it's data, I want to find this kind of thing. But it's very hard because there's so many different data sets and many different...
Right.
Yeah, I
And the
mean,
most
mining
closest one that I have in my mind is the IBM Watson that takes care of the natural language processing, and based on because
so does it use neural networks?
yeah, it's entire deep learning. IBM Watson is entire neural network. It's a-
IBM Watson does lots.
Really? No.
Well,
I doubt it. I mean,
No,
just to
even
give you,
research-
IBM
research.
Watson did everything, but it could not understand what is stuff.
Yeah, there's lots of problems with Watson.
So, well,
Well, I mean,
like I
I mean,
said,
I
it's
don't
all-
think that's the problem.
everybody's
all in-
going crazy about neural networks again now. As deep
Yeah, I
learning.
mean,
sure.
Right.
Air Force is spending
was-
$100 million
It was
on
been
deep
around,
learning.
it keeps, things keep, every 20 years they go to the top again.
Now everyone is AI, I don't know what
But
is new
usually
in AI.
because of the bigger computers and stuff, they work better.
Right.
So that's happened with the
So what is new in
the
AI
parallel
that
algorithms,
everyone
the
is
distributed
talking about?
databases. They've been around for 20
okay,
years.
so it's about
then they
the,
suddenly jump
like I
more
said, it's
cores.
about the
Few more
dimensionality of not just the input data, but if you just, the way I showed you the models, you see how there were different layers and different neurons, right? What they were trying to do, if you know about anything about PCA, principal component analysis, which it tries to take the juice of the entire data set, right? So if you've got a data set of 50 dimension, you just want to reduce it into 10 dimension, it will take those features which has the highest variation, right? That's what neural network is trying to see, and it's very hard to imagine and see how the numbers are behaving in such a large dimensions. So an image which is of 784 pixels, okay, set in a row, is going through a neural network which just has 5 neurons. What it is actually doing, it's actually pushing or combining all those 784 vectors into 5 neurons that can present them as well as they can. So it's just taking the most important principal components of the entire data set, which can be combined together in as low form as they can. So it's basically data reduction, data dimension. Okay.
So do these people also believe our human brains work like that? Because we don't have
No,
any problem
no.
with pictures.
No, no.
Even if you just show the nose of a person, you can tell who it is. I mean,
You know what, sir? The biggest advantage of having neural networks against any other machine learning is, I'll give you an example. You need to have k-nearest neighbors in order to do classification, right? For k-nearest neighbors, to do classification, you will always have to have data set with you, no matter how old that model is. How many times you have, trained that model. With neural networks, you train the model once, you forget about the data, because now the weights have been adjusted with the neurons. You don't need the model again.
but if the data set changes in the future, that prediction will also change. Whether it is neural network or other things, if the data set changes drastically,
Right.
because it is trained for whatever data set with whatever cross-validation you do. So I think that problem will be true for any system.
Yeah, that is true. That is
Any
true.
system.
But they are just trying to overcome that situation where we have large amount of data for which we do not have even good amount of machines to hold them. For neural networks, that is not the
There
case.
is also some other new C coupled or some C neural network. I've been hearing that at Air Force and some people were working on it for essentially image processing. Those people are crazy about.
Right.
One of the things that he brought up was, and that you're talking about now, is this removing certain attributes and
Yeah.
trying this, and PCI is doing that somewhat, right? I mean, PCI is trying to find those things that have the greatest.
Right.
impact,
I don't know
right?
for what reason it did not come to my mind. But
But
yeah,
about
looking.
Yeah,
Dimensionality reduction.
yeah.
Yeah, this common.
Yeah.
Well, that's what he was, I mean, essentially, that's what Sean was talking
Yeah, I mean that validates whether your
Yeah.
your conclusion is valid or.
about. So are you
or-
doing something like that to reduce I mean, you could expand your dimensions easily. I mean, you
Right.
could do it hour by hour and things like that, and then try to reduce it with PCI.
There are different ways. I can do several things that I want with this, but the biggest challenge right now is the amount of data that I have. The second challenge is nobody's ready to share the data set. We even tried. I was talking
So the
about.
UK data set or Microsoft workstation, is it public?
It's public. It's public. We can do. Of course, we can do, and we still are doing it. We still.
I mean, to me, okay, so to me this is the thing. So you have done all this, you have done, so the question is, can you generalize your intuition and work to another problem, or do we have to go through the same steps without knowing anything? That is the biggest problem.
Right.
I mean, that is nothing to do with you.
Right. Right.
It is the problem in general
That's
with some of this stuff.
So there's a data set called Where's George that tracks dollar bills.
Oh, okay.
Have you seen this?
I think I have worked on a subset of that data set.
Yeah.
Just
So it's called Where's George, and looks through a bunch of dollar bills going across
Right.
the US.
Right.
Ah.
Which is kind of,
So what is the